Let me start recording this. Okay. Yeah. So the course on physics and technology of thin films is quite fascinating because I'll tell you why. Today, thin films are used in every electronic appliance. You can't have an electronic appliance without a material used in a thin film form or in the form of a heterostructure, right? For all the devices, the material has to be obtained in a crystalline thin film form. So why do you need a course to understand how materials are obtained in thin film form? So if you take solid state materials, we have hundreds of thousands of solid state materials now. You can name materials giving rise to magnetic properties, electronic properties, superconducting properties, ferroelectrics, piezoelectrics, and optically transparent materials. Hundreds of thousands. So if you take a handbook of transparent conducting materials, which is so essential for many device applications, for photovoltaics, for touch screens, right? You need a transparent conducting oxide in the form of a thin layer. So if you look at the CRC handbook, you'll see, a thick 1,000-volume book on any of these materials: magnetism, superconductivity, materials exhibiting semiconducting behavior, semiconductors, handbook on semiconductors, for example. They run into hundreds of pages with large number of systems listed there, because this is all like 50, 60 years of research on all these materials. Okay. Now you get the material in different forms. So first of all, even before you understand the theory of solids, how solids form, what is the band structure, because the physical properties depend on the band structure, right? There has to be certain knowledge on the band structure of materials. Otherwise, you will not understand anything about the physical properties. Okay, all these different properties I talked about: electrical properties, magnetic properties, optical properties, thermal properties. And what happens to these properties when you get them in different forms is the next big question. So you take, say, for example, a piece of silicon. You take it in a highly crystalline form, a single crystalline form, and a not so crystalline form, what you call it the polycrystalline form. Not at all crystalline form, that is amorphous form, and in thin film form. Now I've already mentioned about 4 different forms of the same material. What will happen to the a given physical property of the same material in all these different forms? So this is with respect to one property. Materials can exhibit large number of properties. There are some basic built-in bulk properties. Specific heat is a bulk property. Electrical conductivity is a bulk property. Magnetic susceptibility, optical reflectance, refractive index, dielectric constant, piezoelectric coefficient. All these are what are called the bulk properties. But you obtain the material in a highly crystalline form, in a non-crystalline form. In between, there are other forms also. Do these forms have any bearing on these physical properties? Is an important issue. First of all, so which means you need to know in how many different forms a material can form. And when you get the material in different forms, what will happen to its physical properties? But then for that, you need to understand what are the basic physical properties that one has to consider if you're looking at talking about changes in physical properties a particular physical parameter as a function of the the form I talked about. So this is where a basic knowledge of solid state physics is very essential. So I'll certainly give introductory lectures, a few, wherever it is required, at least with respect to, if I'm talking about, say, an electrical property, I need to talk about how semiconducting properties come in a given system. And then we look at the dependence of the form of the material on these properties. Okay. But then all these handbooks of materials giving rise to different properties I'm talking about, you have thousands, hundreds of thousands of materials. Even if you take a handbook of semiconductors, hundreds of thousands, right? Similarly, magnetic systems, superconductors. But we are lucky that all these hundreds of thousands of material systems crystallize into 7 crystal forms. Look, where is the physical property of a material coming from? When we say that this material is a semiconductor or an insulator or a superconductor, or it has a magnetic property, where is this property coming from? Or if you say it's a dielectric, right? Where is the dielectric property coming from? Or where is a magnetic property coming from? If I have a magnetic material, if I have a dielectric material, in one case I have magnetic dipoles, in the other case I have electric dipoles, right? So the physical properties basically come from the basic building blocks, which are the unit cells. You know that unit cell is a basic building block, and unit cell is the imaginary cell in which atoms are arranged in a regular periodic fashion, right? So the simplest way in which atoms form is 8 atoms sitting at the 8 corners of a cube. Okay, that's a simple cube. So there are other ways in which atoms can be arranged. So first is 8 atoms sitting at 8 corners, and second, imagine with 8 atoms sitting at 8 corners, you also have an additional atom sitting at the center of the cube. So I distinguish the first one, which is, I call it the simple cube, with the next one where one additional atom is sitting in the middle of the cube as a body-centered cube. And then you have the face-centered cube, etc., etc. So this is a basic building block. The crystal structure is a basic building block, the unit cell. And you also know the unit cell dimensions are at the nanoscale level. And you have so when you talk about a solid finally forms when all these unit cells, have a periodic symmetry, periodic arrangement in the 3-dimensional space. So that's the crux of the whole thing. How these unit cells translate themselves into a perfect symmetric 3-dimensional body determines the physical properties. Then that's where the periodic potential concept comes in, the interaction between atoms, and then how the electrons attached to these atoms behave. So a solid giving rise to a magnetic property that has a magnetic dipole, and the one that is giving you an electrical property, or dielectric property, it has an electric dipole. Everything comes from the unit cell. That's a basic building block. But then you need to have certain number of these unit cells in order for us to start seeing the Coulombic interactions, the long range effects, right? So solid state physics, to understand about material properties, band theory is very important. And to go there, first you need to know what are the different forms of materials, how to get these materials. And before you go in to understand about the physical properties, the most important thing is you need to know how the atoms in a given materials are arranged in a given fashion. So that's what I was telling. Of all these hundreds of thousands of materials that we know giving rise to various properties, these hundreds of thousands of materials, they fall into 7 crystal forms, right? Crystallography itself, in every solid state physics course, crystallography concepts are taught. You take any solid state physics book, the first chapter is on crystallography. Solid state physics book by Charles Kittle, Ashcroft and Mermin, any solid state physics book, or any book on electronic properties of materials. The first chapter is crystallography, because the basis for material properties is the crystal formation. Without that, you won't understand anything. Okay. But then I was trying to say that all these hundreds of thousands of materials that give rise to various properties, various interesting properties, they crystallize into one of the 7 crystal forms only. And you have what are called 14 Bravais lattices, right? Subforms of these 7 crystal structures, 7 crystal forms, 14 Bravais lattices. And then you have 230 space groups, what are called space groups. If you do a regular crystallography course, you'll understand what are space groups, point groups and all that. But as a student learning solid state physics, condensed matter physics, a course like this, electronic property of materials, thin films, a very basic understanding of crystallography is sufficient, because in terms of orientation of the so-called unit cells in a thin film, you need to understand crystallography, which means the basis for crystallography is diffraction, right? So we are actually celebrating 100 years of crystallography, after which only we came to realize how atoms are arranged in a given solid. You should try to understand that materials are there ever since the universe was born. There are actually studies done, and they found that our universe formed nearly 13.77 billion years back. 13.77 billion years back. And then it took nearly, so everything was, there was a Big Bang, everything was in a completely gaseous state. So when studies were conducted to find when actually a neutral atom was formed, it's very interesting. It took another 180,000 years for the neutral atoms to form from all this gaseous state. So that means the neutral atom formed 180,000 years after the Big Bang. Now, 180,000 years is a very, very small fraction of 13.77 billion years. So neutral atoms are as old as the universe. You should always remember this. Okay. Then some of the beautiful studies by NASA revealed that the initial form of the universe clearly consisted of small particles of carbon and selenium. So carbon again is one of the oldest entities, and everything is made up of carbon. We are made up of carbon. Okay, so it's very interesting that a neutral atom that was formed so many billion years back, which also makes up the matter that we know of, right? A solid is a matter. Of course, now we know that solids are made up of atoms, and these atoms are arranged in a particular periodic fashion. But then, since when did we come to know about the fact that atoms actually sit in this particular way? Today I can say, oh, this is a unit cell configuration. So I have a body-centered cube. I have 8 atoms sitting at 8 corners and one at the body center. How do I know that? The wonderful thing, even though neutral atoms formed several years back, billions of years back, until the advent of X-rays, we could never know how these atoms are formed into lattices. This is very exciting, is it not? See, you have the optical radiation. In mid 1800, we had this information about the Lyman, Balmer, Paschen, Brackett, and Fund series that clearly gave us information about how radiation emission happens in visible range, ultraviolet range, infrared range. Okay. Now the concept of light scattering also came almost 200 years back. Even Michael Faraday talked about scattering of light from colloidal particles when he gave those public lectures in mid 1800. And he explained the process of scattering based on Mee's theory. Mee's theory is again one of the oldest theories of scattering. But then, so the way light reflects from, the concept of reflection, refraction of light. Okay. But then the other parts of the electromagnetic spectrum came up. Now the question is, we have a unit cell where the atoms are separated by very small distances. I have 2 atoms separated by 1, 2 to 3 to 5 angstroms, right? And that's a kind of, you call it the unit cell parameter. Okay? The side length of a cube, for example, could be 3 to 5 to 8 angstroms. But then how do I find out that these atoms are actually sitting apart by such a small distance? I cannot use the optical radiation. We have the visible range of the electromagnetic spectrum, where the wavelength range is from 400 to 700 nanometers, 4,000 to 7,000 angstroms. So when you have to measure dimensions of the order of a few angstroms, I can't use the radiation, which has a wavelength much larger than the distance of separation between 2 atoms. So you needed radiation that has a matching dimensionality, right? The wavelength of the radiation should be matching with the dimension of the solid's unit, that is the unit cell. So by then it was also known that which means what? That radiation will be more high in energy, right? Lower the wavelength, higher the energy. So then in the beginning of the 20th century, Röntgen, by accident, he found X-rays because he didn't know what those rays are, because they're not visible. Visible radiation is known. So he named them as X-rays, unknown rays. That's how the name came. But then it almost took 10 to 15 years for people to start doing experiments with those X-rays. So it was the father and son, both the scientists, Bragg, who constructed a source for generating X-rays. Today we know all this is very simple, but not 100 years back. The first tube was constructed with a lot of difficulty because you needed vacuum to construct an X-ray tube. And vacuum plays a crucial, major role in thin film technology. Without vacuum science and technology, there's no thin film growth. See the connection. Okay. So they built the X-ray tube, they produced X-rays. In the initial stages, there were also problems about dealing with the radiation effects of these X-rays. Today, we have all safety measures in place. Not during those days. Not even during the days when I did my PhD, 30 years back. Of course, to prevent the person from getting X-ray exposed to X-rays when you are using X-rays for diffraction, you know, special lead blocks are used to absorb the radiation. Otherwise, it's a very deadly radiation because you're going from normal visible radiation to the next high energy ultraviolet radiation to X-rays to gamma rays, right? So it's the energy increases in that order: UV, X-rays, and gamma rays. Gamma ray sources are much more difficult to handle and much more deadly. So they made the first X-ray tube. They produced X-rays. Finding out X-rays is also a difficult task in those days. Then they had to build X-ray detection counters, right? The Geiger-Müller counters were built. Today's X-ray sources are so powerful. Even one photon can be detected so effectively. So what was done later? So 15 years after X-rays were invented, the Bragg's father and son, they started using X-rays. They knew that it was X-rays with wavelength ranges all the way from 0.1 to 100 angstroms, right? 100 angstroms is again on the higher side compared to the unit cell dimensions. So you can also tune the X-ray wavelength depending on the input power that you give to produce X-rays. Today we use X-rays in medicine. When we go to the doctor with a broken bone to the hospital, he'll use X-rays of certain wavelength. These are soft X-rays, right? Because if hard X-rays are used, they'll ionize the tissues inside the body, which is harmful to the body. That's why X-ray exposure, while bone X-rays are taken, the exposure time is very small. But then you need high energy X-rays when you to get information about the dimensions of these unit cells, right? Unit cells where the atoms are sitting from each other, separated by just a few angstroms. So it was the Bragg father and son who did the initial experiments using the X-rays, and they came out with the concept of X-ray diffraction. So they came out with this famous Bragg's law: 2d sine theta is equal to n lambda, where d is the interatomic spacing. That's what you need to find. When you find the interatomic spacing, you get information about how far the atoms are separated from each other. And you can see that in the formula. You also have lambda. Lambda is the X-ray wavelength. So we use what are called characteristic X-ray wavelengths. And it is such a deep field now: X-ray crystallography, X-ray diffraction, X-ray scattering. If you're a crystallographer, normally you'll be doing 3 courses in crystallography: the basic one, the advanced one, and 2. Like we do statistical physics 1, 2, 3, quantum 1 and 2, advanced quantum mechanics, right? Classic. Then you have condensed matter physics itself is condensed matter 1, 2, and advanced condensed matter physics. These are really oceans. But if you understand basics of crystallography, it is very much essential when you're doing a course on thin films, or for that matter, materials. Even to understand the theoretical aspects of materials these days, right? The basic crystallography, the crystal structure aspects are required. So that's the beauty about the invention of X-rays. Now, the importance of this discovery is the Bragg father and son showed that yes, the way light gets reflected from surfaces, X-rays also get reflected from atoms. But then it's a phenomenon. You cannot call it reflection from atoms. So that's why the term diffraction is used. So it's a X-ray diffraction. In some special cases, we can also call it X-ray scattering also. And there's a revolution today in terms of X-ray sources, the power of X-ray machines, the software that goes into reforming refining the crystal structures, the detectors on the other side to detect even very small signals. It's just amazing. But it took 100 years for scientists and engineers to work together to get extraordinary X-ray machines. So why I said all this is the atoms that were formed billions of years back, and we also know that matter is made up of atoms. A solid contains atoms, and these atoms are formed in a regular, some periodic form. That arrangement of atoms could be understood only after the invention of X-rays 100 years back. So that's why we are 2 years back, it was 100 years of X-ray crystallography. It plays such a crucial role now because today we are talking about a monolayer of coating. I have a base material, a substrate on which a thin film is coated. We have methods to coat a single layer of unit cells. That is called a monolayer. How do I know that I have one single set of atoms or unit cells sitting in a periodic way on a given substrate? I need crystallography. No other way, right? Diffraction. So diffraction can be done with X-rays. Then diffraction can be done with electrons also. Electron diffraction is also there. This is again a very interesting and important field when characterizing materials. For thin films also, electron diffraction is very much essential. Electrons normally are used for in microscopy. So we have electron microscopes. Again, they are so powerful. Today we can use electron microscopes and go down to the level of atoms and see how the atoms are sitting in the lattice planes. That's the kind of resolution you can get using electron microscopy. Atomic level resolutions you can get. And using the same electrons, in addition to getting atomic level resolution and imaging, we can also get information in the form of electron diffraction. Electron diffraction. Again, 60, 70 years of developments. In the first electron microscope came with a magnification of 40,000 times. By the way, if you're using a lens, magnifying lens, and you want to try to magnify any object, you get a magnification of about 50 to 100 times. Then you know these microscopes that you must have used in your labs, starting from the school level. An optical microscope can give you, a small optical microscope can give you a magnification of about 150 to 200 times. But then a little powerful optical microscope can give you 1,000, 2,000, 2,500 times of magnification. But so if I have a solid, if I want to really go down and see at one point what is the magnification, how even the Forget about the atomic arrangement. There's what is called the substructure. How the substructure is, 2000, 2500 magnification is not sufficient. That's when the need for electron microscopes came in. So the first electron microscope, so using electrons, you can get images of surfaces from certain points in a magnified way. This is electron microscope. So using electron microscope, I can get a magnification of the first microscope that came almost 5 decades ago. Had a magnification of maximum of 20 to 40,000 times, 40,000 times. 40,000 times is also not sufficient for you to go down to the level of substructure. Forget about atomic structure. Today, now, after 50 years of electron microscopy, we have electron microscopes so powerful that you get magnifications of few million times. That means if the electron is falling on the surface of a material, imagine I can also focus the electron and I have a small spot, and at the point where the electron is impinging, that part of the material can be magnified to a few million times, which means you can actually go and see the way atoms are arranged. Wonderful. So the most powerful microscope in the world, there are just 4 of them. I mean, this is just to test the limits of electron microscopy, right? That's how science and engineering work together. You have the scientific concept to show that you can generate electrons with these lowest wavelengths, but then if I use these accelerating voltages, I should be able to get these ultimate magnifications and resolutions. Can that be tested? But these are very expensive, but for the sake of testing, you need to do it. So there are 4 such extreme microscopes. Today, electron microscopes are there in every department and every lab. Not like in the earlier days where X-ray diffraction is basically, even X-ray diffraction used to be a central facility. Today, X-ray diffractometers are there almost in every department, 1, 2, or 3 maybe units. Similarly, electron microscopes are plenty. But then these ultimate electron microscopes are just few in the world. This is just to test the limits of magnifications that can be achieved. So the 1100 keV microscope, if you put a silicon wafer, something like this. So this is of course a crystal. See, this is a silicon wafer, shiny, beautiful, single crystalline silicon wafer. Okay. Now, if I put it in the path of electrons in an electron microscope, you go down to the level of seeing the p orbitals, the dumbbell-shaped p orbitals. It's amazing, right? So this is a progress that we have all seen, and the progress that material science has made is really extraordinary. So today, as I mentioned to you, every appliance uses materials in thin film form. So in this course, you'll understand, see what I showed you here is a single crystal silicon. There is a very long process to grow silicon into single crystalline form. And of course, you know the applications of silicon. Without these silicon wafers, there's no microelectronics industry wouldn't have existed. But then growing silicon in this crystalline wafer form is one thing. To make a device, there are so many other layers that come on top of it. To make, say, a field effect transistor, a MOSFET, a touchscreen device, right? So I can use this as a base material, which I call it the substrate on which the other layers come. So that means what? So the same silicon which is in this crystalline form can be also grown in a thin layer form. So while silicon is grown using single crystal growth methods, if I want to get the same silicon in a layered form, I need to use the thin film growth methods. So these are broadly categorized as physical vapor deposition and chemical vapor deposition methods. There are tens of those wonderful methods. Some of them can be done very easily at the lab level. Some of them are very sophisticated, right? Today, if you look at the complete 70 plus inch flat panel TV, these 70 plus inches of the area is coated with thin layers using the techniques that are available now. That's a kind of technological advancement we are seeing. On the other side, why do you need a material in a thin film form? Because ideally, if you take any solid state physics electronic materials textbook, where you see all the physical properties listed, like electrical property, transparency, dielectric properties, these are all the physical properties measured on the physical form of the material. Is it not? So when you do these measurements, you need to do all these measurements on good crystalline form of the material. So the best is to get the material in a single crystal form, where you have periodicity extended on all three dimensions. But then thermodynamics doesn't allow the formation of single crystals of all the material systems into large volumes. So that puts an impediment on utilizing single crystals of a given material. I know that a given material can be used as in nonlinear optical applications, but then you can't grow it into a certain volume that you want it to grow to do the application. So the best way is to grow it in a single crystalline thin film form, because thin film growth is a non-equilibrium process. It doesn't care about thermodynamics. But of course, in terms of reducing the device volume, weight, see that your mobile is so thin today. It's because all these 15, 20 different devices that are inside are thin film based. That's one thing. So you also need thin films in a crystalline form to do very authentic physical property studies. This is very important. I want to measure a physical property on a crystalline form of a material where it's not easy to grow the single crystal. Then I grow it in a thin film form, in a crystalline form, and I do all the measurements, right? So I'll stop there. So tomorrow I'll start again. So we'll meet at